All right, so the one thing that I just wanted to go over from this slide that I did not go over previously was this x1 and this x2. What are those x1 and those x2s, and why must those be whole numbers? Well, remember this p hat 1.52 had to come from a sample divided by the sample size, or your number of successes divided by your sample size to get 0.52. So in order to get that x1, you want to take your total sample size times the percentage of successes in order to give you the number of people that said they approved of the job rating of Obama. And the same thing is going to be true over here. So you're going to want to make sure that you take that 1,500 times the 0.46 to give you 690. And when you do this on the calculator, those have to be whole numbers, because think about it, you couldn't have a quarter of a person or a half of a person. So if it does end up being a decimal, just make sure that you round it. It will not make a big difference in your final answer. Okay, so now based on your interval, is there convincing evidence that Obama's job approval rating has changed? Now, here was our final answer, 0.03 to 0.09. Now let's think about this. If there was no change, then that means the approval ratings would be the same for both years. If there's no change, then p hat 1 minus p hat 2 would be 0. Okay, notice here, this confidence interval doesn't have 0. It's not included. So we have convincing evidence that the approval rating has changed from October 2012 to 2013. Because notice, we would say, oh, the true difference in proportions is between 3 and 9%, or 90% confident that it's in there. So in 0 is not even a possibility. Now, I would highly suggest doing this on your graphing calculator. It's going to make your life easy. All you have to do for the free response sections is to make sure you plug in the numbers correctly so that we see it on your paper, but get the calculations from your graphing calculator. If you would like to see a video explanation, go to Blackboard, go to course content at the top. There's a calculator folder. Okay, so what you're going to do is you're going to hit stat, go over to tests. Okay, you're going to scroll all the way down to B, where it says 2 proportion Z interval. That's why it's important to know the name of the test. We have a 2 sample, we're talking about proportions, and it has to be Z. Now notice here on your calculator, it doesn't say, hey, what are your percentages? No, it says how many successes were there. So here you're going to take that 1,500 times 0.52 to get this number, 1,500 times 0.46 to get this number. If your calculator says error, it means that for x1 and x2, you did not have whole numbers. They cannot be decimals, so just be aware of that. Confidence level is 90%, and it creates the confidence interval for you. Done. Love it. Notice how your P1 hat and P hat 2 match what we were given in the problem, because they took and did 780 divided by 1,500, 690 divided by 1,500. Remember to use this as a check and to get your final answer for your free response. Always use it for your multiple choice section. Much easier. Now, what exactly do the significance tests look like? In this case, for our significance test, we're checking to see if there's an observed difference between the 2 sample proportions, okay? Are the two population proportions the same? Are they different? Or is one bigger or is one smaller? You're going to have to make your null and alternative hypothesis based on that information. The null hypothesis is we're always assuming there's no difference in the proportions. So if there's no difference, that means it's when you subtract them, you're going to get 0, or that they're equal to each other. Now, like I said, it's important to make sure you define P1 and P2 so that we know what proportions we're comparing. We're not going to be, maybe we're comparing proportion of iPhones, proportion of TVs in your household. So that's important that you define that. And also notice we have no numbers here. Why do we have no numbers? We have no numbers because keep in mind that we are dealing with a sample in order to estimate the population. So we don't know the population. So that's why we're leaving it in just in terms of P1 and P2, which are your parameter. Just like in our single sample, these will always be in terms of the population. The alternative hypothesis is, hey, what difference do we expect to see? So either proportion 1 is bigger than proportion 2, and you don't have to write greater than 0. I often just write P1 is greater than P2, okay? Or is it less than P2? Is P1 less than P2? When you subtract them, the difference is negative. Or are they not equal? P1 is not equal to P2. We don't know what direction it's in. We just know they're not equal. Okay? Now, keep in mind, once again, cannot state this enough, that the null alternative are always in terms of the population proportion and not the sample. For a test of significance, we are assuming that the difference is 0. And the alternative says, hey, we don't think they're 0, we think they're something else. Okay, so what exactly how are we going to do your tests, your two-sample z-tests for proportions? Okay, so in our null, we're assuming that the two population parameters or proportions are the same. We call their common value P. We need a way to estimate P, so in this case only, it makes sense to combine the data from the two samples. We are going to pool our sample proportions. Okay, so this is a little bit tricky. What this means is when we use the standard deviation, we're not going to use two separate proportions, proportion 1 and proportion 2. We're going to use what we call the pooled proportion. Why do we do this? It gives us an overall proportion of successes in the combined samples. That way, we get a more precise estimate of the difference in proportions when we use more data. Now, all pooled means is you have two samples, you take their total successes and add them by the total sample size. So it's pool just means combine. Combine your samples over combine the sample size. Okay, when will you use this pooled value? Never, ever, ever, ever for confidence intervals. You'll use it for the standard error and finding the standard deviation of the statistic. You'll use it for checking the normal condition. And I say to do this before you even start the problem, label it and put it at the top of your calculations so that you know that's what you're using for your standard deviation and for your normal condition. Okay, so conditions, same thing as they were for your confidence intervals. Simple random sample, we have to have independent random sets, which is different than our independent condition. Make sure you're stating 2 times. Simple random sample of data set 1, simple random sample of data set 2. Now this independence condition is used for your standard deviation. We're making sure that the population is 10 times the sample size for both of them. Okay, so be careful that you do it for each of them. And then your normal condition, notice you have n times your pooled value is greater than 10, n times 1 minus your pool value is greater than 10. 2 samples, 2 independent samples, have to do this twice. Okay, so what does your test statistic look like? Now, remember our test statistic has the same formula every single solitary time. We're always going to do the statistic minus the parameter divided by your standard deviation. Now, in this case, we don't have a single p-hat. Since we have 2 samples and we're subtracting them, that statistic actually becomes p-hat 1 minus p-hat 2. So you want to be a little bit careful with that. Okay, now where's this 0 come from? Minus the parameter of 0. All right, we're subtracting 0 as the parameter because we're assuming there's no difference in the proportion. So remember that null when we said that P1 equals P2 or P1 minus P2 is equal to 0. Okay, that's where that 0 comes from. We're assuming the parameter is 0. And then the standard deviation of the statistic is what we talked about previously. Okay, now notice, same thing as our confidence interval standard deviation of the statistic, except for this portion right here. Okay, we're using that pooled value, okay, in order to, we're using our pooled value instead of our separate proportions, okay? Instead of our separate p hat values, we're using the same p hat value twice, all over sample size 1 and sample size 2. Okay, so what exactly are your critical z's or your hypothesis going to look like? So let's say we're doing our hypothesis test with P1 minus P2 is equal to 0, and we find our z statistic. So keep in mind, once again, this is your statistic, the difference in proportions. 0 is your parameter, assuming that there's no difference. When you calculate the p-value, remember your p-value is the probability of getting a z statistic this large or larger in the directions specified by the alternative. Now, if your alternative says P1 minus P2 is greater than 0, then you're going to do the probability that z is greater than something. Okay, that's what it's going to look like on your curve. If you're doing the probability that P1 is less than P2, then you're finding the probability that your statistic is less than something. What is it less than that number? If they're not equal to, remember, we don't know if it's above or below. So let's just say z is 1.5. We're going to find the probability that z is greater than 1.5, and then the other one is the complete opposite. Z is less than negative 1.5. And that's what these absolute value signs. That just means we're taking the absolute value of your test statistic, what's the probability higher, lower, or remember when you do this, these two probabilities are going to be the same because your graph is symmetrical. You can take 2 times the probability that z is greater than 1.5, and that will give you the same answer. Okay, so just as a note, to wrap up everything we just talked about, remember confidence intervals are in terms of p hat 1 and p hat 2. Tests of significance for the standard error are in terms of that pooled estimate, okay? And remember, that's literally you just adding your successes together from both samples over both sample sizes. The name of this test of significance is 2 sample, because I have 2 sample, z-score, test, because I'm doing a test and not an interval, and proportions, because I have proportions and not an sample, or sorry, not a mean. You're going to get your p-value from the calculator, and how is your conclusion going to look different, okay? Now, it's the same wording as the confidence interval that we've already talked about. So this is important to state, if the true difference in proportions, you just don't want to say if the true proportion was this, because that's not what we're testing. We're testing to see if there's a true difference in proportions. All right, let's take a look at this question and see how we do. Are teenagers really going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 to 2006, 19.5 showed some hearing loss. Do these data give convincing evidence that the proportion with teens with hearing loss has increased? Now, please keep in mind that this question is a test of significance, not a confidence interval, because we just want to see if it's increased. We're not estimating how much it's increased. So try it on your own and see if you can do it. All right, let's go over the answer. Let's see how you did. Okay, remember the state is always in terms of the population. We're checking to see if the data provides convincing evidence that the proportion of teens with hearing loss has decreased at the 0.05 level. Level wasn't given, so that's what you assume. Okay, we're using a 2 sample z-test for proportions. Do that pooled value right at the very beginning so you have it and you don't have to worry about it. So here's where our number of successes from each sample, 351 and 450. And then here were our sample sizes, 1,800 and 3,000. And this 0.167 is just from you adding the numerators, dividing by the entire denominator. Simple random sample of 2 samples. And you also need to state that they are independent random samples. Okay, your independence condition, make sure you do it for both conditions, and your approximately normal, you also have to do for both conditions. Okay, and notice that we're using the 0.167 1 minus 0.167 from your pool.